Thanks everyone for coming. I'm happy to introduce the speakers for the high energy seminar of this week. So the first speaker is Marko, sorry, and ask you pronunciation, Ristić. Marko Ristić, postdoctoral research associate at the Rochester Institute of Technology, where he recently defended his PhD under the guidance of Professor Richard O's. Thank you. Previously, he studied particle physics at CERN, then laser characterization for the Virgo collaboration at the University of Tor Vergata in Rome. And then I learned here that he attached also his first external privately owned instrument on the WIN 0.9 meters telescope in Tucson, Arizona. So his PhD research focuses on Kilonovae modeling and creating surrogate models for the parameter inference applications. In addition to research, Marko is highly involved in K-12 and undergraduate mentoring and outreach, and is also American Physical Society Career Mentoring Fellow, and also National Mentoring Community Mentor. Through this, he educates students about career path offered to physics bachelor degrees holders, and also offers accessible one-on-one academic advising to students belonging to the underrepresented groups instead. Everything goes okay with the microphone. I'm reading the title of the presentation today. It is leveraging machine learning to enable Bayesian inference of Kilonovae model, Kilonovae using detailed models. Just let me see.
Yeah, you want to use it?
Oh,
And the other one works.
oh, you're trying to get this one to work?
Okay.
Yes, I'll be right back.
Sure. Thank you.
And with that, the floor is yours.
Thanks, Rodríguez. Yes, so I'm Marko Ristić. I come from Rochester Institute of Technology in Rochester, New York. That's an hour east of Buffalo. And I work closely with collaborators at the Los Alamos National Lab on, exactly as Federico has stated, Bayesian inference of Kilonovae using detailed models allowed using machine learning. And so to give a little bit of context, what I'm looking at are neutron star mergers, right? So here I'm showing snapshots of a simulation video, looking at a top-down view of the end stages of a neutron star merger in spiral. On the left, you can see the log color density of the two stars, and that's the first frame. The second frame, we see the beginning of the actual merger, where there's a lot of significant deformation of the stars themselves, preparing for the third slide, where we see lots of matter ejection surrounding this merger remnant here, which in this instance is a black hole. And so the part that I'm really focusing on is this third slide, where we have this mass ejection. There's a lot of the material that kind of settles into this accretion disk surrounding the merger remnant, but a lot of it also flies out into space. So that's what I'm interested in. And these are great astrophysical laboratories for understanding, for example, the origins of the elements. I'll talk about that in a second. And, for example, the dense matter equation of state, which I'll touch on a little bit at the end of the talk, and many other very interesting science problems. So the conditions in the post-merge environment are perfect. They're very hot, they're dense, and they're very neutron-rich for what is called the rapid neutron capture process, or the R process. And what we have happen basically is we have some seed nucleus here on the left that's capturing a lot of these free neutrons. And what that creates is a kind of unstable nucleus that's going to want to decay towards stability. This radioactive nucleus then undergoes beta minus decay, in which one of these overabundant neutrons turns into a proton, an electron, and an antineutrino, which we see here, the electron flying off. And the key thing to note is that this decay process is happening in a much slower time scale than the actual neutron capture process. So you're going to have this reservoir of neutrons in the nucleus for this process to happen over and over and over again. So as you're creating these protons in the nucleus, you're creating new elements going down the periodic table. And like I said, some of these are going to be stable, a lot of these are going to be unstable and radioactive. And so because we're going to have this very large population of very different radioactive nuclei, what we actually get is heating on different timescales, which creates an astrophysical transient, and that's our kilonova. And so here on the left are light curves. The points are observational data of a detection that was made in 2017 of Kilonovae AP 2017 GFO. This has been the first kind of confirmed kilonova in that it was also detected using gravitational waves to confirm that it was indeed the merger of two neutron stars. And from this transient, there were a lot of initial modeling efforts. One is from this paper by Ashley Villar, where many people were very interested in modeling this emission and kind of understanding what's going on. And from these initial modeling efforts, there came a kind of general consensus that two separate ejecta components were required to properly hit the kilonova emission. One is it's frequently referred to as the blue kilonova, and this is a less opaque component comprised of weak R process elements, which basically means that the ejecta there is not as neutron rich, and therefore it's not going as far down the periodic table, which means that it becomes transparent to photons sooner. And so that's going to dominate much of the early kind of bluer emission. And then the second component is the red kilonova, and this comes from what is the main R process component. This has elements such as the lanthanides and actinides, which you may have heard of, which contribute significantly to opacities and therefore only become transparent at later times, where we see kind of these redder bands in the infrared emitting. And so since then, there have been a lot of modeling efforts. And kind of nowadays, you can pick one of what I'm going to talk about two routes specifically, where we consider either simplified models or radiative transfer models. And both have their benefits and drawbacks. For simplified models, for example, these were initially very useful because they allowed very broad parameter coverage, and they kind of they allowed us to look at all the possibilities that a kilonova could have while being computationally efficient. So you could run a bunch of models for a bunch of different parameters, and it wouldn't take very long. So this is great for like a survey. Of course, the drawback is that there's limited physics output because in making simplifications or assumptions or approximations, these are not going to have as rich of a physics yield. Radiative transfer simulations, on the other hand, radiative transfer modeling has very detailed microphysics treatments. You can learn a lot more about the physical processes that are going on. And you can explore, for example, if you're looking at spectra, salient features that kind of tell you about maybe even what some of the elements are in the kilonova. However, they're very expensive in terms of applications to Bayesian inference. You can't run 1 million radiative transfer models in the same time that you can run 1 million simplified models. So what my work does is it focuses on how to actually make this limiting step easier or remove it altogether. And so enter machine learning, which I'm going to just briefly go over here in a simple 1D explanation of Gaussian processes, where for some arbitrary inputs x, we have some function that characterizes these inputs f of x. And if we give no constraints as to what this function has to be, there's an infinite family of functions that can characterize our arbitrary inputs. However, if we add two quote-unquote simulations where we say for these given inputs, the function has to evaluate to these values, then what we see the Gaussian process do is it kind of says, okay, so I know that this has to be the answer at these points. And as I get further away, my uncertainty is going to increase. So the idea is if we can kind of figure out a way to place these points, these simulations, in the most optimal way possible, we can get information about kind of the global function scale using as few of these expensive radiative transfer simulations as possible. And that's exactly what I did. So I started with this kind of initial grid of simulations, pretty sparse, kind of covering the general range of input parameters. And I employed an active learning scheme where basically it was choosing the next simulation intelligently by finding where the region of uncertainty was largest and placing new simulations there. And we ended up with this simulation grid at the end. So this doesn't exactly tell you very much. And I'm more than happy to talk in detail about how the active learning worked. But the idea is, okay, so we have a bunch of these simulations. Now, do they actually achieve the desired effect? Because we want to use these as the training set for our surrogate model. And here's showing exactly the fact that we did succeed. So What I'm showing here is if we take one of these simulations from the training set and leave it off to the side, and we train the Gaussian process on the rest of them, we know the inputs for this simulation that we placed off to the side. So if we feed those to the Gaussian process, does it reproduce what we get from the simulation? And the fact that you can't really see the difference between the Gaussian process prediction, which is a solid line, and the simulation output, which is the dashed line, shows in fact that we are able to do off-sample interpolation. So really what this is saying is that we've created some kind of surrogate model which takes our simulations and is able to generate outputs without having seen those simulations beforehand. And that's great. Now we want to apply that to actually something that we can observe. And the way we do that, real quick primer, Bayesian inference, right? Bayes theorem. For our likelihood, we just use a simple Gaussian likelihood. Here written in the log form. For our priors, typically, if we have uninformed priors, we use a uniform prior distribution, or if we have some information, we just assume a normal. For our likelihood, it's for our marginal distribution, sorry, that's just a normalization factor, so I'm not going to go into that. And what we get out are these posterior distributions. So the posteriors are telling us basically, okay, here are the most likely values that we expect for our parameters. And so what we get are these light curves. So again, this is the same observational data that I showed before. And now we're showing the best fit of our models to this data using the Gaussian process that I trained. And on the right, I'm showing the posteriors for our parameters. The first two columns are the masses of each of the two components. The second columns are the velocities, and then we also have viewing angle, which is important because we're not assuming spherical symmetry. And so the reason why, for example, we're interested in things like the mass of the ejecta is because this directly ties into things like our process enrichment of the Milky Way galaxy, where we're looking at how much events like neutron star mergers contribute to our process elements in our galaxy. We also then looked at spectra, because I said, radiant transfer simulations are useful for understanding spectra. And here we're showing just a simple two-component fit. So again, nothing has changed. We're still using the same library of simulations that we used for the light curves, and we just trained a different surrogate model for the spectra as well. And what is shown here is, so at one day, we have 10 different spectra that we fit to. I'm only showing 4 for brevity. But at one day, the fit is pretty decent. At 4 days, it's still quite good. There's this little gap here that persists into 7 days as well, but the majority of the spectrum is fit decently well. And then at 10 days, the spectrum is rather noisy in this region and peaks at later times. So we're more interested in this, where it's got pretty good agreement. Before I get into the next part, I should also mention, so before we go into kind of this next quote unquote issue that we're seeing, with these kind of two inference approaches where we use the light curves and the spectra, we find pretty good consistent agreement in the masses of the two components that we get back. So here what I'm showing are for each of our 10 spectra, the predicted masses in the mass plane of the two components as the cyan dots. Their average is the red line, and that corresponds pretty well with the posteriors that we got for the masses from the light curves, right? Except what we also get pretty consistently is this kind of region where in the G band, past about 3 days, our model is pretty underluminous compared to the data. And we also, like I said, see that in the spectra as well, where in the G band, we're really getting we're missing something, right? There's some kind of energy missing. And so the question is, how do we fix that? And naturally, extending from our existing 2 radioactive heating components, we consider a third component to address this. Now, rather than going through and, like I said, generating a bunch of expensive radiation transfer simulations, what we consider is, okay, let's use a simplified model to kind of guide our understanding of what's going on. And what this simplified model does, basically, it spreads up the ejecta into different shells moving at different velocities. And integrating over these shells, we just get the total luminosity, which gives us the effective temperature through the Stefan-Boltzmann law. And when we plug that into the Planck function, we can get out some black body spectrum. So this is kind of telling us, okay, we we can get some idea for what parameters are going to give us the kind of spectrum that we expect. And this worked really well, so we created this kind of third component, and we added it to our initial 2 component, and this overcame, so the 1-day spectrum didn't change much, but at 4 days, we see much better agreement than we had before. And at 7 days, it's not perfect, but it's getting there. So where we went from here, we said, okay, so what if we take those parameters guided by this simplified model and actually ran this in our radiative transfer simulation with a fully self-consistent 3-component model. And when we did that, we get something quite surprising. So here, just to remind you of what's what, the red is our initial 2-component fit that we were trying to boost the emission of. The purple is our 3-component fit with the added toy model spectrum. And then the blue is our realistic radiative transfer fully self-consistent model. And at 1 day, again, not very interesting. At 4 days, what you can actually see is that the blue, which is our realistic 3-component model, is actually even dimmer than what we started out with. And that was quite surprising because that was the thing that we had set out to undo. And at 10 days, what we can see is the reasoning for this is because we actually get this very large peak at 1.5 microns, which means that a bunch of our photons were actually reprocessed into the infrared. So we had the exact opposite effect of what we wanted to happen. And that's just saying that simplified and realistic models are not interchangeable. So just because they can kind of guide our study doesn't mean they're one-to-one. Now to pivot a little bit, I put up here a picture of classic Where's Waldo. Don't bother looking for Waldo. He's not actually in this. He was removed. And the reason is because Waldo represents our neutron star mergers. And so since 2017, they've only had kind of the one confirmed Kilonovae / neutron star merger. And now the question is, okay, so while we're waiting for the next one, what do we do? And to get kind of the maximum amount of information that we can out of this one really nicely observed detection that we have, we kind of start looking at other ways that we can incorporate observations. And so, for example, for each of our 2 components, before I refer to them as the red and the blue kilonova, just go by the colors, they're both going to have some sort of elemental abundance pattern, right, that characterizes them. And so what we can consider is if we have, for example, on the right here, a chart of masses for one component, masses for the other component, any point on here is going to give you a mass for each component by which you can scale these original abundances and see how well they compare to the solar R-process abundance. And so what we do with what the colors on this right plot are showing is what the residual calculation basically is between the scaled abundances and the solar. And this tells us, what this can tell us basically is that we have this kind of yellow region that's the lowest residual that's saying which mass pairs of the 2 components fit the solar R process the best. That can create what we look at as a mass ratio if we just go along the diagonals of that plot. And then if I overlay this kind of color diagram with the mass posteriors that we got before from our Gaussian processes, initially what we got was this black banana shape, which is telling us, okay, the total mass ejected is constrained. So we know that the total mass, if you go along this band, the total mass is constant. But it could be all dynamical mass, all the red kilonova and no blue, or vice versa up here. So you don't know where you land on here. However, when we incorporate our observations of abundances, we can introduce this additional prior that's going to intersect this yellow band with the black banana shape, and then that's where you get this red dot. There's a caveat, of course, you're not intersecting the whole band, and that's because there's an inference fudge factor that's kind of saying how much you actually trust this additional prior. So if you were to relax that, you would get more overlap with the black band. But this now is telling us, you know, if we trust it a lot, it's pretty confidently telling us, yeah, this is how much each of the 2 components contributed mass-wise, which is much more interesting and stronger result. And finally, in the last minute that I have, just some preliminary work where we can also consider, I mentioned the dense matter equation of state. We can consider what if we don't look starting after the merger itself, but actually start looking at the parameters of the binary that produced the merger. We can start getting some idea about their parameters that relate basically to the radius of the neutron star. And the radius of neutron star we can use as a proxy for the equation of state. And so when we look at, for example, these dashed lines are saying when we sample in gravitational wave parameters or binary parameters, sorry, using and then only use the light curves for analysis, we get very broad posteriors kind of telling us that the radius could be anything. Not quite, but much broader than when we introduce gravitational waveforms into our likelihood, which say, yes, the binary parameters also have to produce a gravitational waveform that matches what we saw for 2017 GFO, or 2017. And then we get these solid lines, which are both globally much more concentrated on a smaller range of values, and also for each of these different fits, they're producing much narrower posteriors. And so I breezed through this very quickly just because I'm running out of time, but I'm more than happy to talk about any of this in more detail. So just to finish up, the takeaway here is not that simplified models are bad by any means. The takeaway is that detailed and simplified models are not interchangeable, and so we just have to be careful when we're applying them, that they're contextually appropriate. Detailed simulations and machine learning go hand in hand. The stuff that I talked about here was for Kilonovae specifically, but these techniques are easily transferable, and so I'm very interested to talk about how this can be applied to other problems. And finally, perhaps unsurprisingly, multiple observational channels are going to yield maximally informative inference while we wait for the next neutron star merger. Thank you.
Thank you very much. Do you have any questions?
Great talk. You talked about using a Gaussian process to do this interpolation between your simulations. I wonder, did you ever consider using another way of this interpolation, like a neural network or something?
So yes, short answer, yes. Long answer, the Gaussian process was largely for the initial set of light curves. This was actually a random forest for the spectra, and that's because it just offers a much finer level of detail. This was also extremely bulky and difficult to store because basically how deep the forest went. And then yes, we've also used the neural network. I think I have some slides. Let's see. Yes, this is with a neural network. Nope, that was the wrong button. Sorry. There we go. Okay, short answer, yes, I'll get to the slide. And it was actually very successful. So you can see that we got quite low MSE, and this actually allowed us to get even better constraints on our parameters. I just didn't focus on that for brevity.
This was really great, Marko. So I'm wondering about that, the inability to capture that excess blue flux. Is there more you can say then about the origins? We know that's there observationally. Do we know it's not a radioactive component? Do we just need that it has to diffuse somewhere in the surface? What can we actually say, if anything?
So many people have tried to kind of figure out what's going on. Many people have looked at a non-radioactive, so an external heating source. So for example, a magnetar kind of depositing energy. Other groups, I believe the Japanese Kilonovae group has also noted that there's this kind of difference in the blue, and they actually, one of the things that we looked into is if you remove certain elements from the ejecta, kind of what happens. And so zirconium happened to be one of the ones that if you remove it, you actually get a huge boost in the blue. But then, so there's many things that can be done to alleviate it. The question is sort of what makes the most physical sense. And it's, I think, a difficult question to ask at the moment, because what if, for example, 2017 GFO was particularly blue? And what if this is not a global property of all Kilonovae, et cetera, et cetera? So there's many things that people have done, many things that have worked, many that have not. It's hard to kind of land on a definitive answer.
Thank you. There are more questions. Curiosity. So at 10 days, the spectrum, last spectrum showed about what's the gamma, what's the bulk speed of the plasma?
Well, oh, I don't know. Let's see. Do I have? actually. I don't remember the per spectrum parameters. Even if I could tell you the speed from our inference at least, the velocity is one of those parameters that I trust the least. And it's just because it's hard to constrain. As for I don't have an answer off the top of my head for how fast it's moving in 10 days. I want to say on the order of probably 0.1 C.
Because this can affect can Doppler shift the spectrum you're showing now. So,
Yes.
so the spectrum you were showing data were not as frames, so you need to.
I believe they're corrected for that.
Okay, with the uncertainty on speed that you're just talking about.
That I don't know. That I don't know.
Okay. Maybe
Yeah.
Okay. All right, thank you. Any more questions? No? If not, let's.
Open.
Sorry.
Since you said you were happy to talk about your active learning thing, you elaborate a little bit on how exactly that worked. So you had an original set of simulations, then you use the Gaussian process to sort of decide where, using the active learning, where to run your next simulation.
Yes.
So how exactly, so what were you trying to reduce the uncertainty across the entire range of the light curve, or what was the criteria?
Yes, so the Gaussian process made a full light curve prediction, and whether you believe that's a smart choice or not is a different story, but it had some sort of global uncertainty on the entire light curve, and so and then we sample from a large combination of parameters and find where the uncertainty is the largest, and then place a new simulation there, retrain the Gaussian process, and keep doing it that way. So there's a global light curve uncertainty, which we don't actually propagate into the inference. When we do the inference, we do a per point Gaussian process, such that we understand kind of which times we trust more than others. But for the placement, for the actual to do some the simulation placement in a way that's kind of guided, you have to kind of treat you don't have to, but the simple way to do it is to kind of treat the whole light curve at the same time, and then do just a global scale uncertainty. Does that make sense?
Thank you. Any more questions? This time I see none, so let's thank Mark again. And, let me go on introducing the second speaker. Thanks for setting this up.
Maybe.
So our second speaker is Anthony Rodríguez. So he's a final year PhD student at Caltech, working with Shriku Karni, and also Gary Vandotri, working was postdoc 1 or 2 years ago here, and Tom Pritz. So he's an NSF fellow, Ford Foundation fellow, and also LST Data Science Program fellow. He works on discovering accreting compact binaries in large optical time domain, and also X-ray surveys. And then he follows them up with the Palomar and Keck observatories. He has worked on microlensing and accretion around young stars in the past, and prior to being Caltech, he was undergraduate at Stanford. And today he's going to talk us about accreting white dwarfs in the multivariable sky. Thanks, Tom. The floor is yours.
Yeah, thank you so much for having me, and thank you all for coming today. Today I'm going to take you on a multi-wavelength and a multi-messenger tour of accreting white dwarfs. And at first glance, you might think, okay, this is a very niche topic. I'm not interested, time to clock out. However, I'll try to convince you that accreting white dwarfs really impact all the way down from planetary scales. What they do is some of these accreting white dwarf systems leave behind helium-dominated, quote-unquote, planets. These are planetary mass objects that have overlap with the uppermost range of planets that we know of. And they're also relevant on galactic scales. So this is an image from the Integral X-ray telescope, and you can see that accreting white dwarfs light up the Milky Way in hard X-rays. And there's actually another even deeper look with NuSTAR that reveals the galactic center is lit up in X-rays by these systems. So to further investigate both of these regimes, I'm a co-I on a JWST proposal to get spectra of these helium-dominated planets. I'm a PI of a Chandra proposal with HETG to try to get high-resolution spectroscopy and identify exactly what accreting white dwarfs light up the Milky Way. Okay, so how do we get to these phenomena? How do we get to these planets and all this accretion lighting up? The answer is binary interaction. Half of all stars are in binaries, as we were informed by George Lucas. And what these binary stars do when they interact, this is what they look like, they transfer mass. This leads to stripped stars, like these planets that are left behind. It leads to type 1a supernovae, regardless of channel, double degenerate or single degenerate channel, you need interaction. And then the most compact binaries, and these pro-GR, those all require interaction to form in one way or another. Okay, so there's white dwarfs. They fall broadly under the category of compact objects. And it's true, the highest energy sources are the stellar mass black holes and the neutron stars. But an argument I want to make is that there's plenty of accreting white dwarfs, and we can do very big population studies with them in ways that are still a bit difficult with the other compact objects. So the nearest accreting black hole that we know of is over a kiloparsec. The nearest known accreting neutron star is about a factor of 3 closer. But we really can just look in the solar neighborhood and find the nearest accreting white dwarf 10 times closer than the nearest neutron star. So now I'm going to get into how these binaries formed, and this will describe basically what they are and what they look like along the way. So all accreting white dwarfs are products of common envelope evolution. And this is when you get unstable mass transfer after one more massive star evolves up the red giant branch and then dumps all of its mass onto the other star. So you begin with detached binaries like this. The white dwarf is in blue, and the donor star is on the right. And then eventually, just due to angular momentum loss, the donor star will fill its Roche lobe, and it'll form sort of an accretion disk around the white dwarf. These tend to form, their CVs are born at orbital periods between 6 to 10 hours. CV stands for cataclysmic variable. So this is still at zero years. So there's magnetic braking from the donor star, which is basically ionized particles leave along the stellar wind. They exert a torque on the system, slow it down, and they bring it closer together. So here you evolve down orbital periods 3, 4, 5 hours, and this is after about 200 mega years. There's a short pause, which may or may not exist. I'm not going to get into the details of this, but there's a transition. Now angular momentum loss is dominated by gravitational wave radiation. You're getting to really more compact systems, like 2-hour orbital periods after about a gig a year. And then this phase is where we see most of these accreting white dwarfs. They're just over an hour orbital periods. And in black are evolutionary models that show that they should reach this period minimum. This period minimum is due to this white dwarf is draining matter from the donor star. And at one point, it drains so much hydrogen that it becomes a brown dwarf. It's no longer able to fuse hydrogen. And actually, on timescales of 7 gigayears is how long it takes for the whole evolution to occur. And at this point, you should get these systems called period bouncers. And these are white dwarf, brown dwarf systems. So at this point, the equation of state has changed from a hydrogen burning to a degenerate star, and most systems should be found here. These are pretty short orbital periods, but they're really low X-ray luminosities, barely visible. You can see this spans 4 orders of magnitude. So it's gone down 4 orders from where we started. There's another set of binaries here that are ultra compact. They're below periods of an hour. I won't get into these a ton right now, but one of the big mysteries behind these is we don't know how they're dominantly produced. Is it a double white dwarf channel? Is it a channel that involves a white dwarf and a sun-like star? I'll answer those questions later in the talk. Okay, so we've got this sort of phase space here, And the biggest problem with surveys of these systems in the past is that different surveys yielded different types of objects. So if you want to look at things up here, they're X-ray bright or optically bright, you can pick them out. Systems here in the middle, they tend to show big outbursts like this. This is a light curve that I'm showing from the Zwicky transient facility. These outbursts are due to the disk switching between an ionized and non-ionized state. But if you look at where the majority of systems are, they're very difficult to identify, or they have been in the past, because they don't outburst in the optical, the light curves look quiescent, and then they're X-ray very faint. That's been a big problem in the past. And the solution to this is actually that all accreting white dwarfs are X-ray emitters, though they may be faint. Systems like this that have a big broad accretion disk generate X-rays in the boundary between the white dwarf and the disk. And then these exotic systems, they're real. This is one of the few examples of just systems in astrophysics where you get stream-to-stream accretion. These are so-called magnetic CDs. These are magnetic white dwarfs where the Alfvén radius stretches so far out that you just can't form a disk. You get direct stream-to-stream accretion. And in these systems, X-rays come from the accretion shock. Okay, so to address all of this, one can use a single discovery tool that involves the X-rays. And I call this the X-ray main sequence. So this is a plot that one can make. It's effectively a color-color diagram that shows optical color versus the ratio of X-ray to optical flux. And these are all points in an XMM Newton Gaia cross-match. This is taking the whole catalog of point sources from XMM and cross-matching it with Gaia, keeping only sources in the Milky Way. All of the compact objects are up there. So in red are all of the accreting white dwarfs, in blue are accreting neutron stars and black holes, and even spider binaries. These are millisecond pulsars irradiating a donor, and these are in cyan there. There's an empirical cut that we can use to get most of the sources. There's actually, this is motivated by a theoretical cut having to do with X-ray saturation of coronally active stars. I'll happy to talk about this offline. But those are not the majority of sources in the X-ray sky. So the majority of sources are indeed young stars, active stars. Those are things that are coronally active and produce X-rays that way. But the really powerful thing about this tool is that it picks out outbursting CDs just as well as a non-outbursting type. They're both above the cut. And it's an incredibly efficient tool. So if you're looking at what to use in the era of big data in astronomy, it's something like this. You've got 25,000 total sources in this parent data set. And if you're looking just for the compact object candidates, you only have to target 200 sources. It's a lot easier to write a telescope proposal when you say you want to target this many sources rather than that many. Okay, and so I showed basically what I did with the XMM Newton catalog. I've done it with Swift and with Chandra, but we're in the era of all sky X-ray surveys. So the old X-ray sky looked something like this. This is one patch of sky that we can see with ROSAT. And that's what it looks like today. So this is with eROSITA, and this just changed in January of this year with the new data release. So it's the eROSITA telescope on board the SRG mission. But then everyone asks me this, like, I thought it stopped taking data. How does eROSITA actually work? Well, I'm going to show you. So eROSITA actually had a nominal 4-year mission where it was supposed to scan the sky 8 times. And it completed 4.4 of those scans. So already half of the mission was completed. eROSITA is in safe mode, but once diplomatic ties can resume, it'll be turned on. So before 2024, there were private catalogs, and I'm showing you a plot of X-ray flux versus optical flux or optical magnitude of one patch of the sky. It's a small patch of the sky, but it's representative of the eROSITA mission. So if we looked at some patch of sky with ROSAT, we would see maybe 100 sources. As of January of this year, with the first all-sky scan being released, this changed to 2,000 sources. Before the end of next year, we're going to get the next public data release from eROSITA, and that'll increase it by a factor of 2. So it'll be 4,000 sources. And then actually sometime in 2026 or 2027, just on the horizon, the full eROSITA 4 scans that were taken will be released, and that'll give us in that same patch of sky a factor of 10 more than ROSAT. Okay, so what can we do with that? We can really enter the renaissance of stellar astrophysics in the context of these big surveys. So the black points I'm showing here, this is the same diagram that I showed before. The black points are an eROSITA plus Gaia survey that I did in the solar neighborhood. So if you want to be in the business of identifying accreting white dwarfs, this is what you had to do before. So in the past, you would just like look in the sky and notice historical variables. SS Cygni, UGEM, all these things that have like a name. Someone identified them 50 to 100 years ago. And that picked out some set of the cataclysmic variables. Some of these systems were outbursting, so you could lead an outbursting survey and pick sort of another subset, but that's already biased because it's different from the other ones that were selected before. Some of these were X-ray sources from other missions like Uhuru, Ariel, ROSAT, that gave you another subset. And even after that, you still miss some of these sources, and it took SDSS to discover them. So actually, in the 100 years that people have been identifying these systems in the solar neighborhood, they haven't been complete, because earlier this year I discovered 2 more. And this is just within 150 parsecs. And these were only possible to discover with eROSITA. So why do all those inhomogeneous surveys when you can just do one? There's relatively few things in astronomy that you can pick as a population with just one technique. But you can do that with accreting white dwarfs. So just draw this line, pick everything above. With eROSITA, you can do it. One of the surprising things that we found was that if you plot a distribution of the X-ray luminosity for sort of older catalogs of CVs, you were biased to the higher X-ray luminosity end. That makes sense because you had flux-limited surveys. Now, if you look at systems in the solar neighborhood, it's shifted by over an order of magnitude. So this says that if you want to conduct a complete survey, right now you have to stick to the local systems. So this is the phase space. The colored points are the systems that identified within 150 parsecs. And what's confirmed with this study is basically that we're now complete to this low X-ray luminosity end. And there's a dearth of these period bouncers. That's been suspected in the past, but this is the first time that we've really been able to confirm it. In this survey, 25% of all CVs have this brown dwarf donor. The theory predicts a much higher number. So there have been these debates over the last 2 decades that say, okay, if these systems, are they destroyed or they disrupted somehow? Maybe accretion becomes unstable, sort of at this period minimum. Something we don't know about angular momentum loss as you evolve all the way down. So this opens up sort of a new theoretical investigation that people can do. And as I mentioned, so there's deeper surveys on the horizon. For now, I've focused on local surveys, but I have an ongoing program with SDSS 5, and that'll target everything out to 1 kiloparsec. With these large spectroscopic surveys like DESI, SDSS 5, WEAVE, it won't be a problem to get all of the thousands of systems that will come out from the full eROSITA catalog. Other sort of exotic subtypes of these accreting white dwarfs can come about from these larger surveys. So I'll talk a little bit about some particularly enlightening sources that have been identified already in these deeper catalogs. And one of them is actually the second nearest ultra compact system of Earth that's eclipsing. So this system has an orbital period of 55 minutes. So by the time you came into this auditorium and you leave, 1 year will have completed on this system. Because the system is eclipsing, you can constrain the masses. And this goes back to that evolutionary channel of these ultra compact systems. We can constrain what that is. So models that predict that it's a white dwarf channel predict these masses and radii. Other models that predict a helium star predict these masses and radii, but then the channels that begin with a white dwarf plus a sun-like star predict sort of these masses and radii, which is what we obtained for that system. And if you look at the mass range, that's that sort of giant planet, brown dwarf regime. And there's a population of about a dozen of these now that we can target. One of the other systems was also very enlightening because this showed us that white dwarfs can sustain strong magnetic fields. These are greater than 1 megagauss. They can sustain those fields for over a gigayear. Just to quickly summarize, I guess, what we found for this system, typically when you look at optical spectroscopy of cataclysmic variables, you'll see emission lines with 2 peaks. That means you have an accretion disk, some part going toward you, some part going away. This system didn't have that, so this indicates that it's an accretion stream that we have feeding matter onto the white dwarf. So this system in these evolutionary tracks is all the way down here, and to get from the period minimum all the way back out there, this is another one of those period bouncers, it takes about 2 gigayears to get from one place to the other. And there's no way around that, and it's thought that the magnetic fields have to originate somewhere up there. So this shows that white dwarfs can be strong magnets for a while. So getting into magnetic field generation with white dwarfs, we understand neutron star magnetism pretty well. We understand low mass star magnetism pretty well. White dwarfs are still very mysterious. We don't quite understand what all of the magnetic channels are for them. One of the most popular models now is that at least for some of these systems, it's a dynamo very similar to the Earth's dynamo that generates a magnetic field on the white dwarf. And what is required for this to happen is for white dwarfs to crystallize. White dwarfs that crystallize tend to be massive and more cool. Once that happens, the carbon-oxygen interior can separate, and it basically acts like a conducting fluid, like the iron core of the Earth, and you're able to generate these magnetic fields. And the reason that this channel has been proposed has been because if you look at the progenitors to these accreting white dwarf systems, you'll find that only 2% of white dwarfs are magnetic. Whereas if you look at the accreting systems that had to come from this phase, 35% of them are magnetic. How do you increase your magnetism by a factor of 70? So this is what's been proposed as the channel. You start with something that does not have a magnetic white dwarf. Enough time passes for the white dwarf to crystallize and for matter to go from the donor star onto the white dwarf. So this has the effect of spinning up the white dwarf. The magnetic field is then generated. This requires a fast spinning white dwarf. And indeed this is how you form the fastest spinning white dwarfs that we know of. So these are in the spin periods of like 20 to 30 seconds. You have the white dwarf eventually start spinning down, and at some point the donor star attaches. This leads to systems that are called white dwarf pulsars. AR-SCO is a famous example of it. And these are systems where synchrotron is generated from the interaction of the donor magnetic field and the white dwarf magnetic field. I've discovered sort of a population of these systems called white dwarf post-pulsars that I call them. I'm not gonna elaborate on them a ton, but they're very similar to these white dwarf pulsars, except that they have longer white dwarf spin periods. So they form another evolutionary step in this process. And eventually the white dwarf slows down and it matches the orbital period like you do in the majority of these systems. So what do we need to test this model and this idea of dynamo theory? So we need to actually identify more of these white dwarf pulsars and propellers. There's only 2 of each class known. We need to find other intermediate phases like we've done for that type of system. And then we need to measure white dwarf masses and temperatures. And those are things that HST can uniquely do. UVEX will help us do that in the 2030s, but for now, we can stick to HST. So I'm going to keep showing plots like this that are flux as a function of distance. And what I'm doing here is I'm creating sort of the worst possible estimate, like the most pessimistic estimate, the lower limits of how many systems we should find with E rho zeta given the current space densities. So with ROSAT, really, there were just a few systems that we could identify of these sort of exotic magnetic white dwarfs. And already in this first survey of Eurozia, there should be, 5 to 6 more. And with the full scan that we have, this will really enable population studies for the first time, so that these predictions yield about 30 of each class. As proof of concept, I've discovered the second fastest spinning white dwarf that we know of. And you can see this in the optical. If you take high cadence optical photometry, you can just pick out the white dwarf spin period in a periodogram, and this thing is spinning at like 27 seconds. One other interesting part of this whole phenomenology is that the radio emissions tend to change over time. So these white dwarf propellers tend to have radio flares. The propellers are white dwarfs that are spinning so fast the material is kicked out rather than accreted onto the white dwarf. So some of those sort of bits of kicking out lead to the radio flares. As I said, white dwarf pulsars, they pulse in the radio. The post pulsars, it's unclear if they pulse or not, but eventually you get down to a phase where they're radio quiet. So there's an emerging class of long period radio transients that sort of occupy this regime of like minutes to hours long periods. And they can be transient and variable, they're concentrated in the galactic plane, and they really stand out from all of the other populations of pulsars. So it could be that in these transitions of going from radio flaring to pulsing to not pulsing, you get some of this very weird radio behavior. It's been thought that those systems are related to white dwarfs because you see the donor star in the spectrum of a few of those long period transients. I'm going to go through this real quick in the last few minutes here and just talk about the multi-messenger side of this, the gravitational wave frontier. So this goes back to those extremely ultra-compact systems, and these are called high-state AMCDNs. And these are the shortest period binary stars. If you just make a histogram of accreting white dwarfs, most of them are CVs and in the long orbital period range, and there's barely any of these. So who cares about these small populations? These make up half of the LISA verification binaries. These are things that when LISA turns on, we'll already have discovered them in the electromagnetic side. LISA can point at them and we can measure their gravitational wave strain. This is just the LISA strain curve. This is the strain as a function of frequency. And you can see that AMCDNs make up nearly half of them. The current ones that we know of, there's very few that we can detect with ROSAT. Same story as the other white dwarfs I've talked about. We can get a few more with ERAS-1, and with the full Eurozeta survey, we're predicting 40 to 50 of these will be seen. As proof of concept, I have a pilot project that's already increased the known population by about 50%. This is what these light curves look like. So on these systems, these have like 17-minute orbital periods. Since I've been talking, this has undergone 2 orbits. And projections of those other systems that will be observed by Eurozeta show that they'll all be very loud LISA sources as well, clustering up above around the verification sources. And with that, I'm going to say the renaissance of stellar astrophysics is here, enabled by the X-rays. Thank you very much.
Thank you. Great talk, thanks. Your questions.
Hi, Doc. How do you distinguish CVs from quiescent neutron star or black hole LMXPs? Very similar luminosities, very similar orbital periods. So let me turn the question around to how many of the known systems show up in the same survey?
Yeah, that's a really great question. So going back to that slide with the XMM catalog. Yeah, so just by like initial mass function arguments, there should be hundreds more of the CVs than neutron stars and black holes. The easiest way to immediately distinguish between the two is with phase resolved spectra. You get enough spectra, measure the RV curve from the donor, and if the velocities aren't high enough, you'll know it's a white dwarf. So that's where SDSS-5 really comes in, and it really helps because SDSS-5 gets time domain spectroscopy. So for a lot of these systems, already with one spectrum, the emission lines aren't broad enough. You know that it's not going to be a super deep potential, so it's probably a CV. But with SDSS-5, you know for sure.
Any more questions?
Do we have any online? No. Okay, now let's thank Tony and those speakers of today. Thank you. So this is the announcement. I remind you that tomorrow, 3 o'clock, we have here a special energy seminar here in Philips Emerging. So don't miss that. Thank you.